Thank you very much. Thank you. I would like to thank the organizers for inviting me. I would like to thank Renaud for giving a great lecture series. And so during which Renaud introduced us to a family of representations of mapping class groups that he qualified as somehow weird and bizarre, but very interesting. So in this talk, I would like to discuss a generalization of these mapping class group representations. I would like to argue that they are also very interesting. And I would even try to convince you a little bit that they're not so weird after all. Maybe Renaud is weird, I don't know. But no, that there is some nice space on which these mapping class groups act and from which you can recover these representations. And so what Renaud defined for us is a family of representations that is originally due to Reshetikhin and Turaev, based on work from Witten. So these are called typically Witten, Reshetikhin, and Turaev representation. I will call them WRT. And they have a bunch of very nice properties, and we saw proofs even of many of them. So as Renaud said, these representations, they preserve a Hermitian pairing. So this was mentioned in the first lecture, but we even saw proof yesterday of the fact that these representations are asymptotically faithful. In the sense that they come in families indexed by well, in the construction, an odd natural number. And if you take this natural number called the level of the theory to be high enough, then every, well, at least for every element of the mapping class group, you can choose a level high enough such that this element will not belong to the kernel of the representation at that level. In other words, the total intersection of these kernels is trivial. At least for the surface of genus greater than 3, or otherwise is very small, it's just the center. And we saw also today that these representations are integral in the sense that we can find explicit lattices in these vector spaces that allow us to restrict, that are invariant under the action of the mapping class group, the projective action of the mapping class group. And so we can restrict coefficients for these representations from the cyclotomic field Q of zeta to the ring of cyclotomic integers. And this is one of the properties that has the most consequences, that allow us, that allow for many applications. As we saw today, it can be used to study kernels of these representations. And concerning kernels, what we saw is that, well, Dehn twists act like matrices of finite order on these vector spaces. Dehn twists have finite order. And so in particular, well, the rth power of every Dehn twist acts trivially on these vector spaces. And this is a property that actually has I mean, this is at the heart of an important conjecture concerning these representations, the AMU conjecture that conjectures that essentially these quantum representations can detect the dynamical nature of diffeomorphisms, that Dehn twists are the only finite order elements under these representations. So this is actually can be seen as a positive, as a nice feature of these representations. But if you care, for instance, about the question of linearity of mapping class groups, which is a well-known question, whether mapping class groups are linear or not, whether there exist faithful representations, this immediately tells you that these quantum representations have no chance of being faithful. So you can find elements in the kernel at every level. So today I would like to discuss a generalization of these representations that is due to Lyubashenko, Kerler, based on work of Henning. So call them Henning's, Kerler, Lyubashenko representations, HKL for short. These representations, just like Reshetikhin Turaev representations, they can be constructed in several different ways. There are many variants of these representations, so I will focus on a specific family today. These representations, they enjoy many of the properties that the previous one enjoy, and some others too. So they also preserve a Hermitian pairing. The WT representations, they preserve a positive definite. Hermitian pairing, while the non-semisimple ones, so the HKL, also called non-semisimple quantum representations, they preserve an indefinite pairing. This is work of Gier, Patureau, Sassen, and Lauda. They are also asymptotically faithful. I will kind of put a check here to signal that both constructions enjoy this property. In fact, these representations, the family I will discuss today, they surject onto these ones, and you can see from this that they are still asymptotically faithful. Today, I would like to tell you a little bit about the integrality of these representations. So this will be the main focus of my talk today. But concerning the last property, what happens in the non-semi-simple case? So maybe I should write this in blue. Say that the blue representations have twists that act as matrices with finite order, and while the red ones, it's never the case. So there is a question related to mapping class group, the one I was mentioning before. Are they linear? There is an open question even concerning these representations. Are HKL representations faithful? So we know that kernels for blue representations, they contain powers of Dehn twists. We have seen also that contained in the subgroup also generated by, so by the Johnson kernel, by N. But for these representations, everything that was known to be in the kernel in the lectures we've seen today is no longer there. So the question is open. And in fact, in genus 1, So I will, so thank you for your question. I will make things precise in a second, because to make things precise, I should say exactly my conventions. Everything today for me will be for a surface with one boundary component, a single boundary component. So I think it is probably something that has been studied by Renaud and Jules in their recent work. And unless I'm mistaken, this, so there are several ways of sending the braid group into the mapping class group. The chains. So I think this one recovers a specialized version of Lorentz representations. But with this specialization, it is not known whether this representation is faithful or not. But you can find faithful braid sub-representations inside these mapping class group representations, just not maybe the one, I mean, I'm not sure which one you're thinking about, but there are braid subgroups that act faithfully in these representations. Maybe Renaud and Jules can tell you something precise. I maybe cannot do that right now, but what I will write down now is that in genus 1, at least, these representations are faithful. So, of course, we already knew that the mapping class group of the torus is linear, but this is a positive sign concerning this specific family of representations. And so today I would like to use to focus on one of these properties, integrality, as an excuse to tell you a little bit about these representations, why I like them, and I will focus on a specific setting. So I will, as I said just now, consider surface sigma g. Actually, so this has been denoted sigma g1 over the past few days. This will be the only surface, so the only kind of surface I will consider. So I will kind of drop the 1. But oh no, oh no. Okay. Oh well. I will probably forget at some point to write it. Just sigma? Just sigma. I will have a G in formulas. Oh my god. Well, okay, I will try. I will try to remember this sigma G1. But let me draw a picture. So this will be the model I will have in mind. I will start from the unit cube. I will do surgery G times along G pairs of disks like this, and this will be my standard model for the surface. And need some notation to state the main result. And this is a notation that magically never appeared over the last week, but it was lurking in the background of, for instance, Renaud's lecture series. So I will consider a quantum group, the quantum group of SL2, the small quantum group of SL2. And zeta here will be a root of unity of odd order. It will more specifically be equal set to e to the 2 pi I over r, and I will take r to be an odd integer. The theory can be developed also for all the other choices of zeta, but I will state some results that have been figured out with precise conventions and precise formulas that only work in this setting, so everything can be adapted. But for today, I will remain in this setting. I will tell you what this small quantum group is. I'm not assuming that you know. For the moment, you should just think about this as a finite dimensional algebra. It is at the heart of the construction of quantum representations. Everything can be stated also in terms just of the Kaufman bracket, but Renault's construction can be reformulated in terms of the semi-simple part, let's say, of the representation theory of this group. We will not need, I will not say too much about this group, but I will give you a definition, and this might seem like some artificial object structure to consider if you just care about class group representations. I would like to argue that this is kind of natural, and that it makes sense that we should consider Hopf algebras like this one if we care about mapping class groups. So I will try to say why. In any case, formally the result of the construction by Henning, Scherer, and Schenko is a family of representations. This will be my notation. They are also projective, just like in the lectures we just saw. What changes here is with respect to Renault's talk, is that the vector space is different, is larger in particular. So in the case of these representations, it will really just be the Gth tensor power of this quantum group. So for a surface of sigma g with one boundary component, the action of the mapping class group is a projective action on the Gth tensor power of this quantum group. And this, as a vector space, is a vector space of dimension r to the power 3. So we have a representation of dimension r to the power 3g. And the theorem I would like to talk about today is this one. Suppose that R is prime. Then there exists a Z zeta lattice, an explicit one. I will not give you explicitly the basis, but they can be given very, very explicitly. They have been, we constructed them explicitly. This is a lattice inside this Gth tensor power. It's a basis, it's an integral basis for this vector space, in the sense that if it's free, if you take the tensor product with q zeta, you recover the original vector space. And this allows you to restrict coefficients of these mapping class group representations. So I will denote this like this. Matrices can be taken to have coefficients in z of zeta, and they fix this lattice. And again, like the reason why we wanted to extend this result to this family of representations is because this property is at the heart of many applications of Witten Reshetikhin Turaev representation. So today I would like to tell you a little bit about this this result over here. Tell you a little bit what this group is, and very quickly, but then tell you about the strategy of the proof. And the strategy of the proof will allow me to mention, well, I will tell you where does this come from. And this is why I believe that these representations are somewhat natural, because it turns out that this quantum group, what did I call this? UQG. It can be embedded. I will call this embedding phi G. Maybe this is too low. I will do this a little below. Too high, not too low. It can be embedded in a big direct sum for all positive integers of homology, twisted homology groups of configuration spaces of this surface sigma G1 relative to some of the boundary of these configuration spaces. I will give details later. We should take twisted coefficients in some vector space. And it turns out that, yes, precisely. Yes, yes. And I will tell you as much as I can about both of these constructions. And the remarkable thing about this embedding, so this is an embedding of vector spaces, but of course this one carries an action of the mapping class group, which is the one here. And it turns out that this also admits a very natural action of the mapping class group of the surface. Well, the mapping class group of the surface acts on its homology here, considering the homology of the configuration space, an configuration space of this surface. The relative part is kind of a technical, I mean, it's just the setting that we considered to obtain this embedding. The action on this homology, at least on the homology of this configuration space with Heisenberg coefficient, was introduced by Blanchet, Martin Palmer, and Awais Shaukat. And here, this is a specialization of that construction. The action on the Heisenberg homology is twisted, and there is an explicit specific way of untwisting the action that will actually make this embedding compatible with respect to the two actions of the mapping class group. This is kind of the remarkable feature of this model. Yes. 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 So this action is defined by Henning, Skeller, and Lubashenko. It comes from a TQFT. I will not have time. So constructing this action properly requires somehow a mini course. Maybe, or I mean, if you really want to see why this construction works and not just formulas. And I will not do that, but I will tell you a little bit where does this come from. You should imagine just that this is at the heart of this construction. There are the same ideas that Renaud used for his construction. You need to generalize these ideas to a setting which is slightly more complicated, so which is yes. Over here, this is rho. This one, as I said, is a different action in nature. So it's defined in purely homological terms. It turns out that this embedding respects these two actions. It respects even more. So it respects even actions of the quantum group of SL2 that exist on both sides. So in other words, the one first way in which you can see the small quantum group of SL2 as some natural structure is as an algebra that acts on the homology of the configuration spaces of these surfaces. And this what is as an yes? Yes. So this is an infinite dimensional that contains, so the action over here is the G tensor power of the adjoint representation of UQSL2 onto itself. This over here is an infinite dimensional space that contains the adjoint representation as the head of the representation, but it's an infinite dimensional module, and it carries also an action of the bigger quantum group of SL2, the one at least considered by Habiro, so the one with divided powers of one of its two generators, F. I will say maybe something more precise later, but essentially, I mean, I don't have a better answer than this for the moment, but I think this quantum SL2 representation deserves to be studied on its own, and it exists also when the deformation parameter Q, that here is called zeta, is not a root of unity. So this is something that exists generically. But I will not really talk about this today. But this embedding here is very explicit. So for instance, when G equals 1, it sends a very simple basis of this quantum group. That I will define later. Well, up to scalar, it sends this to a basis of this homology space that can be explicitly described by drawing curves in the surface. So let me do this. So, yeah. Oops. So this for the moment doesn't mean a lot, but so this is A, this needs to be labeled B. So I'm just claiming that this model allows you to translate elements of the quantum group of SL2 into diagrams made up of curves, systems of curves in the surface. There is a way that I will explain to interpret such a picture as Borel-Moore homology class in this relative homology group. And the action over here is defined using quantum algebra. And over here is a much more natural action from the point of view of topology, because it's just essentially induced by the action of the mapping class group on the homology of the surface. So the theorem that I kind of mentioned already and that is kind of the main tool to prove this other result over here, is that phi g is an isomorphism at least onto its image, onto of representations of both the mapping class group and the small quantum group. And these two actions commute. So the action of the mapping class group is implemented by quantum SL2 intertwiners. So yeah. So how am I doing? Very bad. So I will try to tell you a little bit about the definition of this quantum group. I will try a bit about this other construction. I will try to fill in as many details as I can. And I will probably start from the quantum side. So U zeta SL2 can be defined as the Q zeta algebra with can be given by generators and relations. Generators EF and K, and relations E to the R, F to the R equals 0, K to the R equals 1, and some well-known quantum SL2 relations in their, yes, SL2 relations in the quantum version. Like this. This is, as I defined it right here, is just an algebra. It can be given much more structure, which is used to define these representations. Again, I will not define these representations. I will tell you somehow what is the nature of the definition on the left side, what is the nature of the definition on the right side, and everything. Just know that everything can be made very explicit. In fact, this isomorphism is proved just by performing computations in bases, in these bases, and seeing that the two U zeta SL2 can be given the structure of a, whatever this means, a factorizable Riemann-Hopf algebra. It just means that it doesn't only come with the structure of an but with other pieces of structures, other operations. It has a coproduct, it has an antipode. This is not really crucial for the purposes of this talk. As a basis, sure, of course. Sorry, you're right. I forgot an F. Yeah. Thanks. There's an F here. Also, usually here you have a denominator, but this version of the definition features a renormalized version of F, which contains the denominator that, if you already saw quantum SL2, you usually see appearing here. This is not. This is nothing special. It has a basis given by polynomials like the ones you see there. Is a basis. So it's R to the power 3-dimensional as a vector space. In this basis, you see some new symbols. So 1m is just a linear combination of powers of k. Again, just not really important, but just to explain some of the symbols that were already on the blackboard. And Fn is the it's just a divided power of f. So here there is a quantum integer, which is just a Laurent polynomial in zeta, invertible one. But essentially, this is a basis. So the one I wrote there is a basis in genus 1. So for one tensor copy of quantum SL2. And I will just, so again, I will not have time to define the quantum representation. Let me just tell you the idea, the vague idea, at least the philosophy behind the definition. So the reason why, starting from quantum SL2, you can construct these quantum representations of mapping class group is morally because sigma 1, 1, so the torus with one boundary component, admits itself the structure of a, again, factorizable, whatever this means. It's not really important to know the definition. Is an algebraic structure with some important properties, but it's a factorizable BP. So BP stands for, it's two initials, it stands for Bobcheva-Piergallini. Hopf algebra. In a category, in the category of three-dimensional cobordisms between surfaces with connected boundary. So connected cobordisms between surfaces with connected boundary. And you can really understand the torus itself as a Hopf algebra inside this category, whatever this means. So there is a notion of Hopf algebra in general monoidal category, and the torus is itself the universal factorizable BP Hopf algebra, whatever this means. So the reason why in quantum topology we always choose a quantum group or a Hopf algebra to construct representations is because whenever you have an example of a Hopf algebra that satisfies enough properties, that has enough structure, you can use this to represent the torus and all its friends, all the other surfaces and their mapping class groups using this algebra, this Hopf algebra. So the structure of Hopf algebras is essentially, so their presence in the theory of quantum representations is dictated by the fact that the torus itself is a Hopf algebra. This is not something that is intended to be precise or enlightening. It's just the moral why. So this is just a kind of a explanation of why if you do quantum representations, you end up working with quantum groups and like quantum SL2. Quantum SL2 is kind of easiest example you can consider. And we can use U zeta SL2 to represent it. And if this is vague, it's not because things are necessarily vague. It's just a matter of time. I'm choosing to talk a little bit more about the other half of the story in the time that I have left. Everything can be made very, very precise and explicit. So, for what concerns homological representations, the main message will be that the construction is completely different, but the result will give isomorphic equivalent representations. So to talk about them, we need the configuration spaces of surfaces. So this will be the unordered configuration space of endpoints in the surface sigma G1. So this would be the unordered configuration space. In those homological groups, there is a relative part. The relative part is this one. So configuration space with a boundary minus here is the set of those configurations of points that have at least one coordinate in this boundary minus. What is boundary minus? I will draw it here. Boundary minus is just the red. It's just one interval in the boundary of the surface. So I'm taking configurations of endpoints, so unordered configurations of endpoints in the surface relative to those configurations that feature at least one coordinate in one interval is contained in the boundary of this surface. And there is an important quotient of the fundamental group of this configuration space that is isomorphic to the Heisenberg group that I will denote like this, Hg, that can be described, can be given an explicit presentation. I can talk about this by giving an explicit presentation. It's the group generated by generators sigma, alpha j, and beta j, satisfying a nice list of relations. So essentially, all of these generators commute. Except for alpha j and beta j. So everything commutes among these generators except for alpha j and beta j. Their commutator is sigma to the power -2. And it turns out that this group that I just gave as just defined by a presentation, it's, well, so to be precise, I should say, so it's almost always isomorphic to a quotient of the fundamental group of the configuration space of this surface for at least 3 points of configuration is exactly, so this maybe is when for this, I think for this isomorphism, I think n should be at least 3. Otherwise, it's kind of contained between the second quotient and the third quotient of in the lower central series. And otherwise, there is a subgroup of index 2 of this group that is isomorphic to a quotient when n equals 1. The moral is that essentially this is almost always, for all values of n, the biggest, largest quotient along the lower central series for the fundamental group of this configuration space. This isomorphism doesn't depend upon.
No, I'm saying like there's an in on the bottom of the second.
The G has no, is independent of G.
Yeah. No, it's independent of n. Like the HG doesn't look like. Oh, yes.
Yes. Ah, okay. Sorry. The presentation here.
Yeah.
Sorry. Yes. Right. Yes. So the quotient of this. So this is a definition I gave independently of this fundamental group. The isomorphism, as I so okay, it's not precisely with respect to this quotient, but it's isomorphic to a quotient even when n equals 2. Otherwise, for n equals 3, it's exactly this for n bigger than 3. And when n equals 1, essentially, you only get as a quotient the subgroup generated by sigma 2, sigma squared, and these guys. But yeah, so this is an abstract group, and there is an isomorphism at this point with this quotient. Yes. This is called the Heisenberg group. Yes, exactly. Yes. 10 minutes, okay. So if you consider the homology, the Borel-Moore homology, of this configuration space relative to this portion of its boundary, and with twisted coefficients by this quotient of its fundamental group, then okay, this is isomorphic. This is isomorphic to the homology of the corresponding cover. So we can understand this as really the standard homology of a space, where this denotes the cover. Corresponding to this quotient, and this allows us to talk about homology classes inside these groups by drawing pictures like the one, like that one. So for instance, let me draw an example. In which sense do I understand such a picture as, so, for instance, let me put a label n over here. I claim that this represents a homology class in the nth configuration space, in the homology of the nth configuration space of the surface of genus 1. The idea is just that, well, an interval represents, of course, a homology class of a relative homology class in the surface itself of dimension 1, with part in this relative in this interval, in this red interval. So an arc, and when I put a label n on this picture, I'm actually thinking this interval. I'm replacing it with the configuration space, the unordered configuration space of this interval that is mapped into the unordered configuration space of the surface as prescribed by the image of this embedding. Just by saying that if I have an interval map on this path over here, then whenever I have n distinct non-colliding points on this interval, I can map them here, following the orientation of the arc. And this will embed the configuration space of this interval into the configuration space of this surface. And the configuration space of this interval is an n-dimensional simplex. And if its boundary is here in the red part, it defines a cycle in the Borel-Moore homology of the nth configuration space of the surface. And here I'm talking about a class in the configuration space itself. If I want to talk about a twisted homology class in this cover, I should choose a lift. And this can be done by choosing a path from a base point that I can take here, for instance, any point of the simplex. This chooses for me uniquely a lift into this cover and defines a cycle inside this homology loop. And so, drawing pictures like these, I can talk about twisted homology classes in these homology groups. And we have bases that look like those pictures. So a picture is obtained by labeling a graph onto which the surface retracts and choosing all possible labelings whose sum is exactly equal to the number of configuration points I have in my configuration space. I get a basis of this homology group as a zeta as a module over the group ring of the Heisenberg group. So if you fix, for instance, in that example there, if you fix a plus b to be equal to n, all possible choices give you a basis of the nth homology group. So as n increases there, everything changes. So the dimension of the homology, but also the spaces you're taking the homology of. So the nth configuration space enters the picture there. And although the Heisenberg group, as we said before, is always the same. So I have 3 minutes left. So let me just tell you how so I claimed at the beginning that this model that translates this action of the mapping class group that I didn't define, but that I said comes from well, quantum algebra, from the fact that you can represent the torus using quantum SL2. This model translates this action into much more topological terms. So you can consider a homology class, for instance, represented by a system of curves. You apply the diffeomorphism of the surface to this system of curves, and you will essentially obtain the image under the action of this diffeomorphism of the homology class. Except that if you just do that with the definitions I gave there, you will get twisted action with respect, crossed action with respect to this structure of module over the ring of the Heisenberg group. And there is a way, so yeah, there is a way of making this, turning this into a linear action by specifying, by representing the Heisenberg group. Using some explicit r to the power g dimensional q zeta vector space, right? This action is uniquely determined by, this representation is uniquely determined by the requirement that it should be a simple irreducible representation of this group that sends the generator sigma in that presentation to a scalar precisely equal to minus zeta to the power minus 2. This is called the Schrödinger representation. And the homological action on the homology group you obtain by representing coefficients in the Heisenberg ring is essentially obtained from the natural one by shifting, by correcting the effect on coefficients. Because of course, when the point being that this homology over there, the homology of the cover, admits a natural action by that transformation of the Heisenberg group. And when you act with the mapping class group, you twist coefficients for this action. And you need to untwist them, and this can be done explicitly using, so formally what you do is this, is the following thing. So once you have an element of the mapping class group, and you want to act onto an element here, so since these groups, as I said, are actually free groups, are actually free modules, specializing coefficients is equivalent to taking a tensor product with these new with this representation over here, and so tensor product like this is sent to this new tensor product on the left-hand side, on the side of the homology class in the Heisenberg cover. The action is just given by extending F to the configuration space, coordinate by coordinate, and lifting to the cover, which can be done because this is the cover that corresponds to a characteristic subgroup that is fixed by the action of diffeomorphism, when it's preserved by the action of diffeomorphism. And here you need to define an action where this is given by a certain but very explicit projective action on the coefficient part. This part needs to be corrected to get an honest linear representation by a projective action of the mapping class group onto this same representation over here. And so I will finish with this remark. So everything is said concerning this homological model. So the goal was to show that this model allows you to localize the problem with integrality in a very small portion of the construction, because everything else in this construction is inherently integral. So those homology groups have coefficients in the group ring of the Heisenberg group. Coefficients are integers, integral combinations of linear combinations of elements of the Heisenberg group. This representation over here can be defined easily, naturally, over the ring of cyclotomic integers. The only portion of the construction that requires a priori coefficients in the field, in the cyclotomic field, is this one, this action on coefficients, which we only need if we want to consider this kind of linear version of the action. And once you localize the problem here, then you can essentially try to replicate the computations that Gilmer and Nussbaum did to prove to establish integrality in the semi-simple case, and find explicit basis that so span z zeta lattice of this representation that is invariant under this much simpler action, projective action of the mapping class group. And once you have that, everything is integral, and you get explicit integral basis also for quantum SL2 with respect to both the action of the mapping class group and also the action of quantum SL2. I will stop here, so thanks.